You know that feeling when you're following a set of rules perfectly, and then bam, you hit a glitch where everything just breaks? Well, in the world of math, some equations have exactly that. They have these special points called singularities, where our usual methods just completely fail. Today, we're going to explore a brilliant workaround, a kind of mathematical hack that's designed to find solutions right where the problem seems totally unsolvable.
All right, here's our game plan. We're going to start by seeing exactly why our standard tools fail. Then we'll uncover a really clever clue left behind by the great mathematician Euler. After that, we'll dive into the Frobenius hack itself, break down how it works step by step, and finally, we'll see how the answer it gives us can take on some pretty wild and surprising forms. So, in the world of differential equations, one of our go-to tools is the power series. It's this beautiful, elegant, and super powerful method. Right up until the moment it just isn't. At certain very specific points in an equation, these elegant solutions can just completely fall apart. We call these little trouble spots singular points. And as you can see here, it's basically a point where a key part of the equation, this p of x, goes to 0. And when that happens, you get this cascade of division by zero errors. The analogy of the North Pole on a map is perfect. It's that one spot where our nice, neat grid of longitude lines all crash together and the system just breaks down. That's exactly what's happening to our equation at a singular point.
But here's the really crucial distinction to make. Not all of these glitches are created equal. Some are just chaotic, but others are what we call regular singular points. Yeah, it's still a point of breakdown, but it's a predictable one. It has a hidden structure, a pattern to its failure, and that hidden structure, that's the key we can use to unlock the whole thing.
So how in the world do you deal with a predictable glitch? Well, like so often in math and science, the answer comes from looking at a simpler, older problem, an equation that happened to hold the perfect clue.
And this is it, the Euler equation. Now take a look at its structure. It has these powers of x that kind of mirror the bad behavior of our main problem, but only right at the singular point. It's like a simplified model, a stripped-down version that lets us isolate the glitch so we can study it without all the other distracting complexity. And the way you solve it, it just shows the incredible power of a really good guess. Instead of some super complicated infinite series, you just guess the solution looks something like y equals x to some power, r. And when you plug that simple guess into the equation, something amazing happens. The entire calculus problem just collapses into a simple algebra problem you could solve in high school. It's unbelievably elegant. So that little exponent r turns out to be everything. It's literally the key that tells us how the solution behaves as it gets closer and closer to that tricky singular point. Is the solution going to explode and shoot off to infinity? Is it going to shrink down and vanish to 0? The value of r tells us exactly what's going to happen. And that brings us to the main event. What if? What if we could take that simple, powerful insight from the Euler's equation and combine it with the incredible detail and precision of a full power series? This was the absolute genius move by Ferdinand Frobenius way back in 1874. He didn't pick one method over the other. Instead, he proposed a hybrid, a solution that literally takes the best of both worlds. Okay, so here's the big idea. First, you start with that x to the power of r term. That's the part we just borrowed from the Euler equation. Think of this as our specialist, right? This is the piece of our solution that's designed specifically to handle all the messy behavior happening right at the singular point. And then you multiply that specialist part by a standard, well-behaved power series. This second part, the series, that handles all the fine-tuning. It captures the solution's behavior away from the glitch. This brilliant hybrid guess is what we call the Frobenius series, and it's the key that's going to unlock this whole problem. Okay, so we have this brilliant hybrid guess. It's part x to the r, part power series. But how do we actually find the values for that exponent r and all of those coefficients in the series? Well, thankfully, the whole process breaks down into two very clear steps. So here's the playbook. Step 1, we've got to find those magic exponents, the values for r. We do that by plugging our whole hybrid series into the original equation and seeing what pops out. Then, step 2, we use those values of r to find a kind of recipe, a formula, that lets us generate all the other coefficients in the series, one after the other. So that first step gives us this thing called the indicial equation. And hey, if it looks a little familiar, it should. It's basically the same simple quadratic equation that we got from the Euler equation earlier. Solving it gives us two possible values for our key exponent, which we'll call R1 and R2. These two little numbers are going to be the foundation for everything else we do.
Then, step 2 gives us the recurrence relation. Now, this is the recipe we were talking about. It's a formula that basically says, hey, if you want to find any coefficient in the series, just take the one right before it and do this quick calculation. It sets off a chain reaction that just builds the entire infinite solution for us, piece by piece.
Okay, so we have our two roots from the indicial equation, R1 and R2. Now, finding the first solution using one of these roots is usually pretty straightforward. But the real story, and this is where things get really interesting, is how the relationship between those two roots completely dictates what the second solution is going to look like.
Check this out. The whole structure of our final answer just hinges on the difference between those two roots we found. In case 1, if the roots are different and don't differ by a whole number, life is simple. You just get two nice standard Frobenius solutions. But look at case 2. If the roots are identical, the math forces a weird logarithm term to just appear in the second solution. Same thing for case 3. If they differ by an integer, that logarithm might show up again. So those initial roots, they don't just give us a starting point. They literally predict the entire shape of our final answer.
So when you step back, the method of Frobenius is so much more than just a clever math trick. It's a really powerful way of thinking. It teaches us to look directly at the point where everything seems to break, right at the singularity, because often that's where the most important information is actually hiding. It literally turns a bug into a feature. And that leaves us with a final thought to chew on. Where else in science, or even in life, do the trickiest problems, the points of breakdown, actually hold the key to the most interesting answers?